Okay, so this video continues our 9.9 notes on representations of functions with power series. So we're on example 5 here. All right. And basically we're going to continue with the idea of make the function fit that format of the sum of a geometric series. Now, when it says find a power series for the function 1 over x centered at 1, all right, we could do this with the Taylor or Maclaurin series, right? Because all Taylor and Maclaurin series are power series, but I want to come at this from a different angle, right? The whole making it fit the format type thing. Okay, so, all right, currently we have f of x equal to 1 over x, but we want it centered at 1. So first, let's fix the center. But again, we can't just do that. We can't just subtract 1 and pretend like nothing happened, right? So we have to sort of add that back in to the denominator. We have to rebalance our denominator. So let's just rearrange some things so they look the way we want them to. Normally, our next step would be to make 1 1 again, but 1 is already 1, so we've won. And we can move right on to that last step of making it, a over 1 minus r. And there we are. Man, I am punny today. All right, so, all right, from here, all right, we can see that a is 1, r is this piece. Okay, so our power series is going to be, all right, by definition, from n equals 0 to infinity, all right, a times r to the n. So that's 1, I'm not going to write that, times r to the n. And you know me, I like to, if it's alternating, make it look like it's alternating. So I'm going to make it look like it's alternating. So I'll call that negative 1 to the n, x minus 1 to the n. Okay, and if we had done like a Taylor or Maclaurin series, well, this wouldn't be a Maclaurin series because it's centered at 1, so it would be a Taylor series centered at 1. Probably would have gotten the same thing. All right, so now this time we will actually go through and identify the interval of convergence. All right, so for that, let's work in red because why not? All right, so, all right, to get the interval of convergence, we first need the radius of convergence, all right? Meaning we need to find the common ratio of our terms, which is, sure, let's just use the ratio test. Ratio test works for everything. All right, so this is going to be the limit as n goes to infinity. You don't have to use the ratio test here. It can be a little simpler. All right, but I'm just going to go ahead and do it. So here is my x minus 1 to the n plus 1, my n plus 1th term, over my nth term. All right, I've taken out the alternating part because it's an absolute value. So this is going to be the limit as n goes to infinity, all right, of, and then you're just going to have an x minus 1 in there, all right? And so that limit, right, is no longer dependent on n. It's just whatever the absolute value of x minus 1 is. And so in order for this to converge, I need my common ratio to be less than 1. So currently, all right, let's sort of, line up where we are here. So currently we are centered at 1. Our radius of convergence is 1. And so then our interval of convergence will be, so let's see, centered at 1, radius 1. So it'll be from 0 to 1. We just need to figure out, are those endpoints included? Okay. All right, so let's go and test the endpoints. All right, so let's test in our series x equal to 0. All right, so if x is equal to 0, what is the series that we generate? We generate, pen please. All right, we generate from n equal 0, negative 1 to the n, all right, negative 1 to the n. Okay, all right, so let's bring that together. I can just as well say that is where I can use exponent rules, right? I can say that that's negative 1 to the 2n. So that is always an even power of -1, so it will always be positive, right? So that's just 1 plus 1 plus 1, et cetera, that diverges. 0 does not come to the convergence party. All right, let's test x equals +1. So when x is equal to +1, we generate -1 to the n times 0 to the n. Okay, so that's this. And we know what the sum of that series is. Sum of that series is 0, which, yeah, totally converges to 0. Okay, so this one gets to come to the convergence party. All right, fantastic. All right, so for the general strategy for finding a power series for a function, this is basically the steps that we outlined and just reviewed in this problem. So I'm not going to take you through that. But what I would like you to do is hold on to this example 5 in your head for when we move on to the next page. All right, so I've basically given up the ghost here with example 6, but it bears going through, okay? Example 6 asks us to find a power series for f of x equals ln x centered at 1. How is this relevant to example 5? Well, so notice, all right, this function is not algebraic, okay? We are never going to make it fit, this format. We're never going to be able to make it look, like this, right? Those are algebraic terms. ln is not algebraic, all right? So that's not going to happen, all right? The other option is to slog through a Maclaurin series, a Taylor series, since we're centered at 1, right? But that's not great either. And then hopefully we sort of latch onto this idea, right? We just found a power series representation for f of x equals 1 over x. So I'm actually going to write that down, okay? We just found out that for f of x equal to 1 over x, centered at 1, the power series is, all right, from n equals 0 to infinity, -1 to the n, x minus 1 to the n. Why is that helpful? Well, first of all, these are centered in the same spot, right? They're both centered at 1, so that's good, right? What's the relationship here? Hopefully by now you've sort of latched onto the idea, oh, the 1 over x, that's the derivative of the natural log of x. So rather than go through the whole process of generating a Taylor series for natural log, why don't we just take the series that we have for 1 over x and integrate it? All right? Because if we integrate 1 over x, we get back to the natural log of x. All right? So from here, let's integrate this thing. I know, isn't that weird? It's like integrating a sum, but okay. And careful, we are integrating with respect to x. Okay? So remember, plus c, I like to do my c plus, all right? And so again, we're going to check our index at the end. I don't think it should be problematic, all right? The negative is not affected. It's just a scalar multiple. It just determines the sign of the term, all right? So this is going to be -1 to the n, and then we're just going to do reverse power rule on our x term. Okay, so now, technically, since we're generating a specific series for a specific function, we should go ahead and figure out what c is going to be, all right? And so then we start thinking, oh geez, how can we go about that? Well, let's think about the function that we are trying to generate, all right? We're trying to approximate the natural log of x. So let's think about some easy points that need to come off of this graph, right? For example, I know, right, if I'm looking at, f of x equals ln x, I know that when x is 1, I should get out 0 because the natural log of 1 is 0. All right, so let's test that. All right, let's put in 1 for x into our series. And I know that when I put in 1 for x, I should get out 0. Okay, so let's do this. This is going to be, and we've actually almost already done this sum here, right? Because this just becomes the sum of 0, right? And so then from here, right, basically you end up with c plus 0 equals 0. So c is 0. Again, I know it sort of ended up being a trivial result, but it's important because that might not always be the case. All right, so at the end of the day, we can say that that the Taylor series, I'm sorry, not the Taylor series, the power series, all right, for ln x, all right, centered at 1, all right, is going to be, okay, n equals 0 to infinity, -1 to the n, x minus 1 to the n plus 1, over n plus 1. And again, we're confident that c is 0, so we're feeling good. All right, so that's a situation where being able to integrate a power series saved us a lot of time. All right, let's do something similar with example 7. All right, so find a power series for arctan x centered at 0. Okay, again, here we are. Oh, geez, the function that we are given is not algebraic. Again, we could, this time it is the Maclaurin series because it's centered at 0, right? We could basically slog our way through the Maclaurin series, or we could be like, wait a minute, the derivative of arctan actually works very beautifully for fitting the format of the sum of a geometric power series, right? Because let's just take a little look here. Pen. All right. If f of x equals arctan x, then f prime, I know this is taking it back, is 1 over 1 plus x squared. And that is just like ripe for the picking in terms of fitting that to a geometric power series. So let's do that, because then we can fit its derivative to a power series and then just integrate it to get back to arctan. All right, so this is a really important technique that I think often falls by the wayside for a lot of students because we get so caught up in just being able to do the thing. And if you see get a power series for arctan x, you're like, okay, I can totally do this, right? And you'll just hoof your way through it. But, work smart, not hard, all right? So keep this on the table as an option at all times, okay? So now, all right, so let's see. Well, we're centered at 0, so that's already taken care of, all right? 1 is 1 already. So basically we just need to get here, right? 1 minus negative x squared. And then we're pretty much good, right? So from there, we can write out the series. All right, a is 1, r is negative x squared to the n, all right? And then again, you know me, I want to make it more obviously alternating. I also want to, instead of doing x squared to the n, I like to just have it as, a linear term in there so that if we were trying to find the interval of convergence, which was not required, it would just be a little bit easier if we had it like this. X to the 2n. Fantastic. All right. So that is the power series for f prime. So now, in order to get to f, we just need to integrate. So f of x will be what we get when we basically integrate this series with respect to x. So again, going to get a c plus, all right? And then, all right, so here's our series. Negatives are unaffected. All right, and now we need to increment the exponent by 1. So here, right, notice we are not incrementing n by 1. The exponent needs to literally be just one more than it was before. So this is going to be an x to the 2n plus 1 type of situation. All right, over that number, right, 2n plus 1. Done. All right, and then I think we should probably go solve for c, right? We know that if we are looking at our function f of x equal to arctan x, let's think about some things, right? Like easy points that are on this graph. Arctan of 0 is 0. So let's make sure that 0, 0 is on our graph. In other words, all right, c plus all of this business evaluated when x is equal to 0 needs to equal 0. Okay, all right, so you sort of see where this is going. The sum of that series is 0. Therefore, in this case, c is 0 as well. So at the end of the day, all right, arctan x, its power series is simply, pardon my awful sigma. I'm not going back though. I'm just not. Okay. All right. Good stuff. All right. So this, right, the last part of this packet is really all about shortcuts, which we love. All right. So this is another one. And actually, there are still more that we've yet to talk about. These are all just like shortcuts and tricks and really awesome things that simplify your life, because a power series, it's just, right, it just generates a polynomial, and polynomials are super easy to work with, especially when it comes to the calculus. All right, so power series give us lots of brilliant shortcuts. It's fantastic. All right, so find the power series for x e to the x centered at 0. Okay, so if we were going to do a Maclaurin series, we would go ahead, right? We would sort of set it up. Then we would have to get a bunch of derivatives, right, and evaluate those derivatives at 0. Okay, I mean, we can totally do that, but it's just annoying, right? Like, think of all the product rule. And product rule, it's not hard. I'd rather not. All right, so technically, all right, and we'll talk about this later, there are going to be a few series whose Taylor, or a few functions, I should say, whose, Maclaurin series you should just kind of know. All right, so e to the x is one of them. All right, we happen to know, all right, and we've derived this before, all right, that e to the x, all right, so that if we have g of x equal to e to the x, so we're basically going to start with this, all right, that is equal to, all right, from n equals 0 to infinity, right, x to the n over n factorial. That should maybe look familiar. All right, so let's just write out a few terms, okay? I mean, it's like we have the series, that's great. All right, but let's just, because it's going to help to think of these in terms of you're a polynomial. All right, so really, okay, so when n equals 0, I get 1. When n equals 1, I get x. When n equals 2, I get x squared over 2 factorial. All right, and then x cubed over 3 factorial, and so on and so forth. All right, so that's just plain old e to the x. So now, let's actually look at f of x, which is just x times g of x, right? X times e to the x. In other words, every single one of the terms in our polynomial expansion for e to the x just gets multiplied by an x. That's it. So guess what? All we're going to have is x plus x squared plus x cubed over 2 plus x to the 4th over 3 factorial, technically, and so on and so forth. And guess what? Coming up with a series for this is pretty easy, right? So let's do this. All right. So f of x will be equal to, all right, well, let's see. All right, we're going to start with n equals 0. All right, or maybe we'll start with n equals 1. I don't know. Let's see. I'm going to save that. All right, so in general, all right, we're going to have an x to the something. All right, on bottom, I think I'm just going to put an n factorial, okay? So that this is going to be my n equals 3 term, n equals 2, n equals 1, n equals 0. Okay, and I mean, there's a couple ways, maybe that you could do this, but I think, so yeah, we will start at n equals 0. And guess what? I just want my exponent to be 1 more than it was. X to the n plus 1. And so notice how we maybe could have taken the shortcut, all right, from here to here. If I am multiplying e to the x by x, I am simply going to have an additional degree, right, in my polynomial. I am literally going to add 1 to every term, right, to the degree, I should say, to every term of my polynomial. That's it. So if you can, right, go right from here to here. All right, but this is sort of a way that you can reason it out. All right. I am going to hold off on doing the interval of convergence. That is something that you can do for yourself, and I recommend that you do it. All right. But that's enough of this for now. Over and out.